Hi there, this is a short video lecture on analyzing the performance of tilted pad thrust bearings. My name is Andreas Almqvist. I work at the Division of Machine Elements at Luleå University of Technology. And this lecture is part of the Advanced Machine Elements course given the autumn semester 2018. The outline of this presentation looks like this. First I'm going to introduce the tilted pad thrust bearing, and then we are going to see what the governing equations are, and then we're going to take a look at the design charts which we can use to optimize and prioritize between load carrying capacity and power loss. To do engine. So where do we find this kind of bearings? For example, in a hydropower generation. So we have the water reservoir, and then we have the penstock leading the water down to the turbine, which makes a rotation of the shaft and drives the generator. Okay, so this system is here on the right side a little bit magnified and dissected in some sense. So we have the turbine, we have the shaft, and we have the generator. And here we have the bearing, the tilted pad thrust bearing. And this is what it typically look like. So this is the series of pads. Okay, in this case it's only 6. Typically in this application they are about 10 to 20, 30 pads, and the size of them is like half a meter times half a meter. So these pads, they can rotate freely on a pivot, either a line pivot or a point pivot. Okay, and the lubricant is dragged over these segments with a rotating collar. Okay, and of course, as you see in this case, this shaft is extended and goes right down through the middle section here in this bearing to connect down to the turbine. Okay, so hopefully the rotation of this collar drags the lubricant on these inclined bearings, and that generates the lift necessary to carry the load. Okay, the load carrying capacity and the power loss, they are due to several things. For example, the geometry wedge effect. And so what is that? Actually the pads, the segments, they have an inclination, and this inclination makes a convergent gap which generates the hydrodynamic lift as the lubricant is dragged over the segment by the collar. There may be fluid structure interaction, and what I mean by this is mechanical deflection of the segments, the collar, and so on. This would be more apparent in the situation where you have a PTFE facing, which is quite a lot more compliant than the steel backing of the segment itself or the steel collar. There may be thermal deflection, and these can be pretty huge and making the pads convex to the film, and that can cause trouble can be detrimental in the sense that it generates cavitation on the exit side of the bearing. We can have a texture that can be beneficial, of course, can be implemented both on the segment itself and on the color. Roughness is something that we can't get rid of. There will always be roughness apparent at some kind of scale, and the roughness is never a good thing for the bearing. Lubricant surface interaction, what I mean by this is that the surface chemistry can generate more or less slip at the surface, and that of course changes the conditions pretty dramatically. Sometimes you want this, you want a small slip to actually reduce the power losses, but in that way you will also reduce the load carrying capacity. So how to model this kind of application? If you have the possibility to use a software like COMSOL Multiphysics, that will allow you to couple a different set of physics. For example, in this case, you probably would like to couple linear elasticity equation, solid mechanics, with convection and conduction, which is going on inside the film and inside the material. And typically you would use the Reynolds equation to govern the fluid flow and the pressure buildup. So Reynolds equation is actually something that Osborne Reynolds obtained long time ago when he made an assumption of a thin film occurring in bearing situation like this. However, if you assume that the bodies are rigid, okay, so if you have steel against steel and you have pretty large conformity between the bodies, then the deflection should not be that big, and probably you can omit it. You can omit solving the linear elasticity equations. And if also you can assume that the thermal effects have little negligible influence, then you have to solve the Reynolds equation only. And what we'll see in the next couple of slides is a model which is based on the Reynolds equation for this type of situation. This simplified model, namely the two-dimensional Reynolds equation in polar coordinates, looks like this. And actually this is posed in dimensionless form. And there you have the film thickness equation, which declares how it changes from the leading edge to the trailing edge. And you have an expression for the non-dimensional pressure, capital P. You have an expression for the non-dimensional film thickness, capital H, non-dimensional radius, capital R, and there is also an expression for the average radius in dimensions. Okay. Okay, let's proceed. Here you see expression for the load carrying capacity, F, in terms of the dimensionless load carrying capacity, F naught. Same with the power loss, E, in terms of the non-dimensional power loss, E naught. So the load carrying capacity is just the integral of the pressure over the bearing segment. And nearly the same with the power loss, it's the integral of the shear stresses times the velocity over the segment. Okay, and you have other expressions too. You have expressions for the temp increase, delta T. You have expressions for the volume flow, Q, and for the pivot point, so in terms of the pivot point radii and pivot point angle, theta P. Now we have come to the thrust pad bearing design charts, and here we see two of them. In each of them we see three curves for three different pad segment angles, and we see how in this case the load carrying capacity and the power loss changes with the pad inclination parameter. So take a look at the curve for the 30-degree segment angle. First, we have a power loss which is decreasing, it reaches a minimum value, then it is increasing again. Okay, looking at the load carrying capacity, we have a load carrying capacity that increases and then decreases again. And here we can see the actual expressions for the load carrying capacity. And there are also more thrust pad bearing design charts, and here is one for the volume flow. It's pretty linear with the inclination angle, and the difference for the three different pad segment angles is not so big. But it's good to know this because it tells you how much lubricant you have to pump to this bearing to get it to separate the pad from the collar to carry the load. And also it has to do with the cooling capacity. These two design charts are for a self-aligning bearing. If you would like to have that, you have to position a pivot point at the perfectly right position. Okay, so in order to do that, for a certain choice of bearing segment angle and a certain inclination of it, you will have to position it in the angular direction theta p some point. Okay, so for example, if you have minimum power loss for the 30-degree segment angle bearing, you should position it about 21 degrees from the leading edge. Yeah? And you should position the radial point at about 0.87 something 2 or so in order to achieve that. Okay, and well, the rest of the curves gives other options, of course. With this slide, I want to illustrate what happens when we change the pad inclination. So what you see here is a bearing with 9 pads, and the segment angle is actually 30 degrees. And when I press now the animation to start, you will see how the inclination of the pad increases, and as it increased, you also probably noticed that the pressure distribution was shifting so that the pressure, the maximum pressure, was moving towards the trailing edge of the bearing. And also you saw the pivot point here marked with an X was also moving towards the trailing edge of the bearing. What you perhaps did not notice was as the inclination increased, we reached the maximum and then it decreased again. A maximum for the load carrying capacity in terms of its dimensionless quantity F node. So you can see that the maximum is somewhere around 155 or so, and it occurs for about 1.5 K, 1.5. And this is matching the graph that we saw, the design chart graphs that we saw before also. Now this maximum load carrying capacity that occurred for value of K equal about 1.5 means that the leading edge of the bearing is actually 1 plus 1.5, i.e. 2.5 times the trailing edge film thickness. And for example, if the trailing edge film thickness is 10 micrometers, then we will have 25 micrometers on the leading edge. If we have a look at the design charts, we see that this value of 1.5 has this maximum in load terms of load carrying capacity, but if the K value is decreased, we see that the load carrying capacity decreases, and if it increases, it also decreases. Okay, moving over to the dimensionless relative power loss, we see that it's not so big difference from K equal 1.5 to its optimum value at K equal 3, about 3. So this will give a pretty decent design choice to maximize for load carrying capacities, nearly minimizes the power losses. If we have done it the other way around, so we minimize the power losses and choosing the K parameter to be 3, then we would have a slightly lower load carrying capacity. Not a huge difference, but somewhat significant difference at least. And that was all. I hope you have enjoyed this short video lecture and that you have gained some kind of basic understanding of the analysis of performance of thrust bearings, tilting pad thrust bearings. Thank you.